Welcome back. In the previous lecture, we gave the statement of mirror descent, the mirror descent theorem, and we worked through the proof. Finally now, as a little bit of reward for ourselves, we're going to go back to our motivating example and see what kind of benefits we get by using mirror descent rather than our previous algorithm, which was just subgradient descent. In other words, what are the benefits by using this non-Euclidean approach? So let's remember our motivating example. The concrete example is that of robust regression. So remember we had, we wanted to minimize something like AX minus B, the one norm of that. And we found that this is L Lipschitz with respect to the one norm, but had a very bad incurred a square root of n, or square root of the dimension, factor to convert to a two-norm Lipschitz statement. But let's see, rather than going into the specific detail example, let's go into something slightly more general. So what I want to do is I want to minimize function f of x subject to x in the simplex in n dimensions. So the simplex in n dimensions is x, all n-dimensional x, such that x is non-negative, positive orthant, and x sums to 1. So it's just this triangle set. And let's also assume that f is bounded with respect to the one norm, is Lipschitz with respect to the one norm. F is L, let's even make it easy for ourselves, is one Lipschitz with respect to the one norm. And equivalently, this is like saying that the gradient or subgradients of f are bounded. So here's the chance to think about it for a second. Am I going to use the one norm here? I'm not. I'm going to use the dual norm of the one norm, which we derived is the infinity norm. So equivalently, this is like saying that this is bounded in the infinity norm by 1, by Lipschitz constant. Why is this, again, why does this particular example make sense here? Why does our robust regression fit exactly into this paradigm? Because if you look at the subdifferential of the L1 function, what is that? That's just the sign of what's inside. So that means that the subdifferential of that is going to be a vector with a bunch of numbers that are between +1 and -1. So indeed, you're going to have control in the infinity bound. But if you try to convert that to an L2 bound, you're going to get very bad result. You're going to incur this square root of n. So let me write this down again. So recall that this implies that the best we can say at this point is that this implies that the two norm is bounded by square root of n, and therefore, as we've said a number of times and motivated our whole foray into mirror descent, the rate of convergence of subgradient descent is going to be something that looks like x0 minus x star in the two norm times L divided by square root of t, but L is going to be forced to be square root of n in this case. So this is going to look like x0 minus x star times square root of n divided by t. So pretty big. So this is really what we're focusing on. We want to know how are we going to reduce this. So one more time writing down what mirror descent algorithm is. Mirror descent tells me that xt plus 1 is the argmin of x in my constraint set of eta gt transpose x plus d phi of x xt. I need to use a phi that's non-Euclidean. If I use phi equal to half Euclidean norm squared, then I'm going to get back exactly my subgradient descent algorithm. So what phi are we going to use? We need the right choice of it. And this is part of the challenge to appropriately implementing and using mirror descent. I need to use something that's appropriate for my geometry here. So I'm going to use phi of x is equal to the sum of xi log xi, which is just the negative entropy. Remember that x is in the simplex, so we can really even interpret this as the entropy, the negative entropy of a probability distribution. So a few things to note. This takes a little bit of calculation to see, but we can check. I'll just write this as a fact. Phi is 1 strongly convex on the simplex with respect to the 1 norm. Remember that phi has to be rho strongly convex with respect to the norm that is the same norm that we use to measure the Lipschitzness of f. That's critical, and if you look back at the proof, you'll see that we required those norms to be compatible in this very specific way. So this tells me that our rho is equal to 1, rho from the bound. What about r squared? That's the other element that goes into the bound. So we know that L is equal to 1, we know that rho is equal to 1, and our r squared, the definition is the Bregman divergence between our initial point and x star, and whatever x star is, I can always initialize. So if we initialize at the point right in the center of the simplex, so if x1 is equal to the point 1 over n, 1 over n, 1 over n, this is the point sitting right in the middle of that triangle, then I can now find an upper bound to whatever x star happens to be. I don't know x star, of course, beforehand. And you can show that this is less than or equal to the log of n. So let's plug in these numbers into our bound. Plugging in to mirror descent result. What does the mirror descent result say? It tells me that f of 1 over t times the sum of xt minus f of x star, my suboptimality, will be upper bounded by r times L times the square root of 2 over rho t. This is my generic result. Let's plug in all our numbers. So we've got that this is less than or equal to square root of 2. R is equal to log n. R is equal to square root of log n. R squared is equal to log n. L is equal to 1. Rho is equal to 1. So this is going to be square root of 2 times square root of log n over t. What are we comparing this to? Compare to what we got for subgradient descent, which was square root of n over t. So this is potentially a huge win. Let's have a look at what mirror descent actually does as an algorithm in this very specific case to see how is it different than projected subgradient descent. So what is mirror descent doing? It should be doing something quite different if it's getting such a dramatically different result. So subgradient descent is doing something easy to visualize. Subgradient descent, actually projected subgradient descent because we're projecting onto the simplex. All it's saying is that xt plus 1 is equal to the projection onto the simplex of xt minus eta times gt. So I take the step, I project back onto the simplex. It turns out that mirror descent is actually doing something significantly different. So let's have a look at the algorithm. Again, the mirror descent algorithm tells me that xt plus 1 is equal to the argmin of x in the simplex of eta gt transpose x plus my proximity term that comes from Bregman divergence, d phi of x, xt. Writing out the optimality conditions, as we've done before, this is the same as writing that 0 is an element of eta gt plus the gradient of phi of xt plus 1 minus the gradient of phi of xt plus the normal cone at xt plus 1. So we can show that xt plus 1, one way to visualize what xt plus 1 is doing, is that it turns out that xt plus 1 is the Bregman projection. I'll say exactly what this is. The Bregman projection of yt plus 1. So in other words, onto x, which in this case is just our simplex. So in other words, xt plus 1 is the argmin of x in the simplex of d phi of x yt plus 1. What is this trying to do? It's looking over all x in the simplex and finding that x which minimizes the Bregman divergence to yt plus 1. That's why I'm calling it the Bregman projection. If phi were equal to half Euclidean norm squared, Bregman divergence would be just our usual Euclidean norm, and this would be our usual projection. Okay, and what is yt plus 1? Yt plus 1 we get just by looking at this portion, looking at the unconstrained version. Yt plus 1 is given by solving this equation if we didn't have any normal cone. So that means that the gradient, it's specified implicitly, the gradient of phi evaluated at yt plus 1 is equal to the gradient of phi evaluated at xt minus eta gt. This is yt plus 1. So what is yt plus 1 in this specific example when phi is the negative entropy? For phi equal to the negative entropy, sum of xi log xi, then we can show that yt plus 1, the ith element of yt plus 1, is equal to the ith element of the previous iterate, xt, adjusted by a multiplicative factor. So let's see what that multiplicative factor is. It's e raised to the minus eta times the gradient of f of xt, the ith element of that. Okay, so let's see what this interpretation is. So yt plus 1, its ith element is the ith element of xt times something. Let's look at what that something is. So this is e to the minus eta times that ith element of the gradient. So this is telling us that if the gradient is positive, then we should shrink xt in order to get yt. If the gradient is negative, then we should increase. So again, how am I getting that? I'm looking at what is inside the exponent. The argument of the exponent, it's minus eta times the gradient. If the gradient is positive, I have minus eta times a positive number. So e to the minus positive, that means that I'm making it smaller. I'm multiplying by something less than 1, so I'm shrinking. If the gradient is negative, then I have e to the minus eta times minus something, or e to the positive, which means that I'm multiplying by something greater than 1. So I'm shrinking or expanding each individual component of xt based on the sign of the gradient. And finally, xt plus 1 is just going to be the normalized version, yt plus 1 of yt plus 1, L1 norm. But the key is to compare this with subgradient descent. It's quite different the way that it works. So what I'm trying to show here is that by doing something very similar, all mirror descent is saying is do a linear approximation, replace your function f by a linear approximation, and minimize that plus a proximity term. By changing the proximity term, you can get dramatically different algorithms and dramatically different results. And that's really what this example shows. We're going to stop here. We'll pick it up next time.